So let's talk about the concept of leading and lagging, which is going to be very important. Maybe you guys heard about it in your handbooks, but right now we're going to talk about it in detail and what does it mean by leading and lagging power factor. So if you guys remember, when we were talking about the power factor and we were talking about the mostly reactive power, I told you that the theta, which is going to be difference of angle between your voltage and current, is important to be considered based on its sign. So whenever you have the negative or positive, you don't have any problem with the active power, but you do have a difference between the reactive power, because that difference is going to show the characteristic of your total load itself. Either it's going to be capacitive or inductive. By the way, when you're talking about inductive, means that it's about the inductor. You see it in motors and transformers, and we were talking about capacitive, it means that it's a capacitor banks or other thing. So capacitor and inductor were two other important components in the circuit rather than the resistive itself. So let's talk about the leading. When we're talking about the leading, means that I, or current, leads the voltage. What does it mean by leading the voltage? It means that you do have two vectors, because as you guys remember, I and V are not going to be just simply two numbers. They're going to be vectors. They have amplitude and magnitude. So for the amplitude, we are talking about, for instance, at this point, we are talking about the voltage itself. By the way, most of the time, voltage is considered as a reference. So whenever we are talking about the voltage, it means that the magnitude of voltage and the amplitude of voltage, and after that be the phase of zero itself. When we are talking about the leading, means that current reaches to its maximum faster than the voltage itself. So it means that at this point, I do have what? I do have my current like this. And as you can see, the angle between these two guys, which is derived at the theta, which is going to be theta V subtracted by theta I, is going to be what? It's going to give you the angle itself. And then by using that in the formula itself, which is related to Q, and your Q is going to be what's less than zero. By the way, one thing that I have to talk about, or I have to mention, is that whenever we are talking about the Q bigger than zero or Q smaller than zero, we are talking about the fact that the one component is absorbing. Whenever you see that the Q is positive, means that the component is absorbing, and whenever the Q is really smaller than zero, means that the component is some kind of producing the power or injecting the reactive power. When we say that the Q is bigger than zero, then our component is going to be what? The component is going to be inductor, and when the Q is smaller than zero, means that Q is negative, it means that our component is going to be capacitor itself. So far we understood the leading, lagging, inductive and capacitive, and after that the positive and negative Q. But how actually we can remember that? Because obviously, again, for me, sometimes it's going to be confusing about leading and lagging. By the way, when we say that leading I leads the voltage, obviously in lagging means that I lags the voltage, right? So when we're talking about the current lags behind the voltage, we are talking about the concept that Eli. So Eli, the Iceman, is going to be very funny, some kind of codes that at first I some kind of against that, but at the end of the day, I found it would be better to some kind of memorize it. It's going to help you to some kind of distinguish between the capacitors and inductors. So when we say that Eli, means that the voltage is going to lead your current. When the voltage leads the current, means that the angle between I and V is going to be positive, and your Q is going to be bigger than zero, right? Whenever we say that ice, means that current leads the voltage, and I and E are going to be just a symbol of current and voltage. I know most of you guys are familiar with V, but sometimes we use it as E. And when I, the current, leads the voltage, means that the sign of theta is going to be smaller than zero, and Q is going to be smaller than zero. Ice, the C is the capacitor, and Eli is the L is going to be inductive. As simple as that. So let's talk about our main formula, some kind of main guy, which is going to be the apparent power itself. So S, as we all remember, is going to be V times I itself, which is just about the amplitude. But what would happen if I would like to find the angle between the LV and I itself? Or what would happen if I would like to find some kind of the complexity or the complex number of S itself? Because as you guys know, S is the combination of the P and Q. P is the real power, and we call it as just a real number, and Q is going to be some kind of imaginary. That's why we do have the S as equals P plus JQ. You guys are familiar with the complex numbers, so you know that the P is the active or real power, and Q which is going to be reactive power. But what we do have this star sign that we call it as conjugate. The reason is going to be in this sentence. Without the complex conjugate, by the way, why we say that I conjugate? means that the angle of I, instead of by being its own value, is going to be multiplied by -1. It means that if you do have positive 30, this conjugate is going to make it as negative 30. If you do have negative 45, this conjugate is going to make it as positive 45. Why we do have that? Because this conjugate is going to make our math would yield a negative phase angle for inductive load. By taking the conjugate and flipping the sign of the current angle, we force inductive loads produce a positive, aligning the math with the universal engineering convention. So the idea behind that is very simple. The thing is that we know that when Q is going to be bigger than 0, means that our system is going to be what? Inductive. So by inductive means that we do have the Eli itself. By Eli means that voltage leads the current. And when voltage leads the current is going to be something like this, right? But at this point, when you see the angle, your angle is going to be bigger than 0. But if we simply just use the V times I itself, our S is going to have the what? Our S is going to have the negative Q, which is going to be against the fact that this guy should be positive itself. At this point, we are talking about what? We are talking about the fact that we use the conjugate in order to just simply make our math just like the real world value itself. That there's no other strange reason behind that, but this is something that it would be better to know. So let's talk about example. Imagine that I do have the voltage. Again, this is the RMS value, this is going to be the angle, this is the RMS value, and this is the angle. So at this point, I do have the voltage at 0 degrees. We can just simply draw that. And then I do have the I as going to be 40 degrees. So what does it mean by that? It simply means that the voltage is going to be over here, and then current is going to be over here. It means that current reaches to its maximum value faster. So at this point, we say that current leads the voltage. By current leads the voltage, we simply see that it means that current leads the voltage, so we know that it should be capacitor. Automatically, when we are talking about the capacitor, obviously Q should be what? Smaller than 0 itself. But when we are trying to calculate the S, and if you just only use the I as positive value, at the end of the day, your Q is going to be positive. That's why we use the V times I conjugate. The conjugate means that you only have to flip the sign of that 40 angle, which is going to be -40. So if you calculate that one, your S is going to be 9600 with the angle of -40 degrees. So it means that if you would like to find the P and Q, you're going to move back and use the formula that we already know, which is going to be V times I, which is going to be 9600 cosine of this value, V times I sine of this value, which is going to give you the active power and reactive power. So at the end of the day, your active power is going to be like this, and your reactive power is going to be like this. Since the Q is negative, for sure we know that we're dealing with the capacitive bank. So the thing that you'll see over here is that when you're talking about the characteristic of a circuit, which is going to be inductive or capacitive, we are not saying that your circuit is going to only have capacitor or inductor itself. We are saying that the amount of capacitor is going to be higher than the amount of your inductor or some kind of resistor. That's why you do have mostly the capacitive rather than what? Rather than just the resistive itself. By the way, the resistive is there. Your resistor is going to make the active power. What? Your capacitor is going to make the reactive power. If we are talking about inductive, the situation would be vice versa. So let's talk about the actual scenario. Let's talk about the real-time scenario. Why we actually care about the power factor itself. Imagine that we do have two different conditions. At the very first point, I do have the consumption side, which is going to be the factory. And for that guy, obviously, we do have the motors, we do have the transformers, we do have inductors, and we do have everything. So obviously, as the power plant, for instance, Nova Scotia Power, or maybe Hydro-Quebec, or whatever it is that, they have to produce this amount of power itself. But as we all know, since this guy has motors and transformers, we just not simply can give it the active power and call it the end of the day. We need to consider the fact that P and Q should be there in order to that factory works fine. So the thing is that in two different scenarios, I do have some kind of different factories that need the 100 kilowatt of active power. However, for one of them, the power factor is going to be 0.95 and another one is going to be 0.6. So what does it mean? It means that based on this amount of active power, I do have Q1 and I do have the Q2. What does it mean by 0.6? The 0.6 means that if I assume that my P is going to be like this and another one is P is going to be like this is going to be P1 and P2, while we know that both of them are the same. Whenever your cosine of theta is going to be smaller, it means that your angle is getting bigger. When your angle is getting bigger, it means that your Q is getting bigger in the comparison of the Q1 and Q2. If your angle is getting better, it's getting bigger, obviously the Q is going to increase. So what does it mean by Q is increased? Because S is going to increase. And what is the problem with that? Means that if I would like to some kind of produce that amount of active power and reactive power, at some point I have to produce this amount of S1, and another point I have to produce this amount of S2. Obviously S1 is way bigger than S2. And if we would like to move that amount of energy through a cable, we need this kind of big cable like this. And if I would like to move that amount of small s, I need a small cable like this. So as you can see, this is about the trade-off itself between this guy and this guy, and just making those massive cables, especially when you are going to be long distance, you're talking about millions of dollars. Don't let you start the fact of maintenance, any fault that could happen, replacing, theft, and any kind of problem with that. But just imagine that the difference between this one and that one, and why that happened, because a factory has the less power factor than this some kind of factor itself. That's why we would like the factories to have the high power factor, because at the end of the day, that high power factor helps us, the transmission planner, or maybe some kind of transmission owner or provider, which is going to be Nova Scotia Power, Hydro-Quebec, or could be anything. It means that they have to spend less amount of money for this specific factory. They can save the money and they can use it for other factories, and everyone would be happy. So whenever you see that the higher currents is going to produce what? Higher losses. This is another important problem that we do have it over here. This higher losses means that larger cable and wasted generation capacity, which is something that we don't like. That's why high amount of power factor is important to us. So if I would like to give you some kind of a very some kind of common solution that factories use in order to compensate that amount of power factor, we are going to reach to a fact of the capacitor banks. So capacitor banks are going to be connected at the location of the load, or maybe somewhere near, because they're going to produce the reactive power. Producing the reactive power means that Q is going to be negative. By being the negative of the Q, this negative Q is going to somehow cancel the positive Q, and then the power factor is going to reduce. Let's see an example, by the way, while we're trying to waste our time, but just explain everything. Imagine that I do have the motor, and this motor requires 500 kilowatt, half of megawatt, and the current power factor is 0.7. By the way, by lagging means what? Means that I, or current, lags the voltage. When I lags the voltage means that it's Eli. And when it's Eli means that I do have the inductive load. So our target is going to be 0.95. It means that I need to reach to 0.95. By reaching to that number means that what? Means that I can somehow reach to the thing that I like. So at the beginning of the point, my Q is going to be positive, but this amount of number is huge. But at the end of the day, I would like to still make it as positive, but I would like to what? I would like to reduce it. How I can reduce it? If I add it with a negative Q. The negative Q comes from the cap bank. But right now the question is, how much actually reactive power do I need? So let's some kind of use the math. Find the initial reactive power. So as we know, the P is going to be what? 500 kilowatt, and we can simply find the Q itself. Why? Because we do have this power factor, so cosine of theta is going to be 0.7, and then my theta is going to be cosine inverse of 0.7. Then when I do have that, I know the relationship between the Q and P based on the power triangle, based on the Pythagorean theorem. You guys know tangent of theta is going to be is going to be Q divided by P. I do have P, I do have the theta, I do have the tangent, so I can find the Q. By the way, I know for a fact that Q is going to be positive. Why? Because it's literally mentioned that you do have the lagging concept. So I do have this amount of Q, as you can see, is a lot, 510 of kilowatt, and then I would like to reach to the actual value that I like, which is going to be 0.95. Again, I have to do the math. I still need the 500 kilowatt, but at this new location, I need the new Q. The new Q is going to be 164 kilowatt. So you can see that 510 just some kind of translated to 164. So it means that between those values, something happens. Part of the Q just got canceled. How this Q is getting canceled? First of all, let's find the number. And how this guy getting canceled? By using the cap bank. Why? Because cap bank is going to produce the Q, and this negative plus that positive is going to give you some kind of this final value that we like, and at the end of the day, everyone would be happy. That's why we use the cap bank itself. So let's talk about another some kind of example, and imagine that I do have the P is going to be 500 kilowatt. At the first point, I had the 0.8 of lagging, and our target is going to be 0.98. Again, when we are talking about the lagging, means that the Q is positive, but the positive, so much positive. I would like to reduce that value. It means that I still would like to have the positive Q, but our target is going to be 0.98. By targeting the 0.98 means that something happened between there and Q reduced so much. How Q can be reduced? By installing the what? Installing the cap bank. You can easily find those values, the old one and new one. It's just based on mathematics. I'm not going to waste our time over that one. But at the end of the day, if my initial variable of the Q was this and the final value was this, I know that the 274 kilowatt of cap bank actually caused this improvement. So let's talk about the real world application. Again, why we're using that? Because when you're talking about the utility grid, those guys would love to see that a factory would only consume the real power, because the reactive power is good, but it's going to increase the S, which is going to be apparent power. If S increases, means that I increases. When I increases, the loss increases, and when the loss increases means that your efficiency is going to decrease so much, and obviously you need some kind of bigger cables. That's why in the factory, where if they do have the motors, and if some kind of power factor is not going to be high enough, for example, it's 0.8, they have to use the cap bank or whatever, some kind of reasonable solution that they do have in their mind in order to compensate this problem itself. So the thing is that the heavy industry runs on obviously three-phase induction motors. And when we are talking about induction motors, they literally say that inductive load, because they rely on the magnetic fields to spin. They are going to inherently highly inductive. Your Q is going to be positive and huge positive. So what's the fix? Obviously, it's going to be so much challenging to replace those some kind of motors. They cost a lot. I mean, it takes a lot of time, so it's not very feasible. Instead of just forcing the utility power plant 50 miles away to generate and transmit those VARs, so obviously not feasible, engineers are going to simply install the cap banks. They are going to cost a little amount of money, but it's going to be very, very less than some kind of building their new lines in order to use another cap banks, or maybe even just replacing the motors itself. So at the end of the day, this capacitor and motor are going to trade the reactive power, and for this going to happen locally. So this means that we are happy, or the power factor is going to increase. The utility is going to happy itself. One thing that I really would like to mention right now, that maybe you don't face it to the future, but when you're talking about the reactive power, this reactive power has a high relationship with the voltage itself. When we are talking about the active power, this guy has a relationship with the frequency itself. So when we are saying that the Q is related to the voltage itself, another important fact that you have to consider that the Q is mostly localized. It means that if you install the cap bank over here and it has the 500, maybe 50 mile of the length between itself and your factory, the amount of the probability of losing reactive power during the line is going to be so high. That's why most of the time either they install the cap bank at the place of the load, which is going to be factory itself, or a place very close to that. So just remember that the reactive power is related to voltage, and it's mostly localized. So at this chapter, we talked about a very, very interesting concept, which was about apparent power. And apparent power combines the active power and reactive power together. Active power is a very common thing. You already know about that, but reactive power is something that is interesting. It is mysterious. Actually, We like it because it's going to help our motors, induction motors, and transformer to work fine, but at the end of the day, we don't like it because having too much of reactive power means that your apparent power is going to be bigger and bigger. Having so much amount of apparent power, like considering the constant amount of voltage and constant amount of active power, is going to increase your amount of current. Increasing the amount of current means that the utility grid, like Nova Scotia Power, they have to make bigger cables. Making a bigger cables means that they have to produce so much amount of money. You do have so much amount of loss, and obviously it's not very feasible, and we don't like it. That's why the power factor should be as close to 1, which is something between 0.95, 0.98. And whenever a facility cannot handle that and cannot tolerate that, they are obligated to use the cap banks. By cap banks, by producing the reactive power, this problem is going to be solved. So thank you very much for watching this video with me. And if you have any kind of question, I will be more than happy to answer that. My name is Mahmoud Kiosari. Thanks for watching this again. Have a super great day, night, whatever. See you around.